Marcel, feel free to share your slides.
Okay, so thank you very much for giving me the opportunity to talk about synergies between nuclear physics and high energy physics. So this is a very broad topic, and what I will present today is just my personal collection, of some of the synergies between the two offices. So what I would like to do is to spend, just one slide on the science, and then I would like to discuss the probes that both offices use, the instruments, the facilities, and then conclude. So if you look at the missions of the offices of nuclear physics and high energy physics, you will see that, both offices would like to understand nature at its most basic form, you know. So already at a very high level, you can see that there's a lot of commonality between the missions of the two offices. Would like to understand the building blocks of matter and how they interact. But the offices, of course, differ in the probes that they use to answer, the fundamental questions that they have. So the probes that they use are I have split up in four categories. One is completing probes, the other one complementary probes, foundational probes, and orthogonal probes. And I hope it will become clear what I mean by that in the next slides when I present this. So first, the completing probes. So one probe that is very prominent in the field of high energy physics is, of course, neutrinos. We have many experiments, short baseline and long baseline programs that are studying neutrinos. And one of the questions that they want to answer is, the mass ordering in the neutrinos. And you can see here below, the sensitivity to the mass ordering as function of here. And Dune, for example, can measure this mass ordering within 3 years with 5 sigma sensitivity. The other one is, you want to measure CP violation in the leptonic sector for neutrons. So you would like to measure the phase of delta CP. And on the right plot here, you see what the sensitivity is for this measurement, covering 50% of the delta CP values with Dune, with this, phased upgrade between 10 and 12 years. But, to be honest, if you really want to understand, all the characteristics and all the properties of a neutrino, this only addresses one side of the coin. To really, develop a full picture of the neutrino is you would like to measure everything. So one parameter, is what is the mass of the neutrino. And measuring the mass of the neutrino really falls under the office of the nuclear physics office. So the nuclear physics office supports Project 8, where they look for an endpoint measurement of the decay of tritium. And the technology that is being used by Project 8 is the cyclotron radiation emission spectroscopy. So here is a recent result from Project 8. They look at the endpoint, and they're able to set a limit on the mass of a neutrino, an upper limit on the mass of the neutrino of 155 electron volts. Now, this is not very compelling yet, not very competitive, but I would like to remind people that this detector is really a detector that you can hold in your hand, and it's a remarkable achievement that they have done that. Now, there are other properties. What is really the fundamental nature of a neutrino? Is it Dirac versus Majorana? And the best probe at the moment to address that question is to detect neutrinoless double beta decay. And this is, again, something that falls under the purview of the Office of Nuclear Physics. So in neutrinoless double beta decay, you have two neutrons that decay at the same time into two electrons, and you don't see any neutrinos in the final state. So this is directly an observation of lepton number violation, and it would indicate that the neutrino is really a fundamental Majorana particle and its own antiparticle. So really, I would say there's a tremendous synergy between nuclear physics and high energy physics to really complete the picture, of, for example, a neutrino. Now, how would you measure this? So in neutrinoless double beta decay, the way you measure that is you only measure the two electrons in the final state. And the energy of the two electrons is at the Q beta beta value of the decay. So you look at the spectrum, and you look for a very, very faint signal that you would like to detect. Now, this is a rare decay. So the lifetime of this decay is longer than the age of the universe. So given that it's so rare, you really have to understand your background very, very accurately. So this holds true actually for all rare event searches, also for dark matter searches. You really have to have an exquisite knowledge of the level spectra and the decay chains of all relevant isotopes that are in your detector. So if you measure a spectrum, you really would like to understand and identify all the peaks that you see, especially very close to the region of interest. Now, to do that, again, you rely on the work that is being done, within the Office of Nuclear Physics. Here I show two examples of prominent decay chains that you need. So the decay chain of thorium-232 or uranium-235, where you have to have an understanding of every final state, in these decay chains. And that really is, what I call here a foundational probe, because this really enables, some of these experiments. Another foundational probe, I think, is just the measurement of the cross sections of neutrino interactions. So on the right, you see the distribution of the neutrino energy for various accelerator-based neutrino experiments. And of course, if you look at IceCube, this goes way out there. But the cross-section of neutrino interactions with the various isotopes has a lot of structure. And to understand this really, falls, I think, in between nuclear physics and high-energy physics. You can have a neutrino that interacts coherently with the whole nucleus, or it can interact, if it probes the nucleus at a higher level with a single particle or with two particles. So there are many processes on many different nuclei that one has to understand. And, again, this is something that really spans nuclear physics and high energy physics. And to get a full understanding of our neutrino oscillation program really depends on understanding these cross sections. So these long baseline experiments, they built very sensitive near detectors exactly to measure, to map these cross sections. And at the moment, it is the limited knowledge of these interactions that is the largest systematic uncertainty in neutrino oscillation measurements to date. Now, talking about, neutrino nucleus interactions. So again, I think, this is a foundational probe to know these cross sections. So because we know that in dark matter experiments, there is an irreducible background that's called the neutrino fog, and it is mainly, given by coherent elastic neutrino nucleus scattering. So what is shown here is a result from the LZ experiment that came out, I think, 2 weeks ago, which sets the world, leading limits on dark matter, above 5 GeV. But they actually see events, and the events that they see, is solar neutrinos from boron-8 decays. So these are really, sevens events from solar neutrinos. And they were able, turn this measurement around and have a 4.5 sigma evidence of coherent elastic neutrino nucleus scattering of boron-8 neutrinos. Now, it is also true that if you scale up these experiments, future large-scale experiments, the ultimate reach of the dark matter search will be limited by the neutrino fog. And because of the scale of the experiments, these experiments, so this high-energy physics experiment looking for dark matter, will also become sensitive to neutrinoless double beta decay. Now, the other interesting twist here is, I think it's an interesting twist, is that you can turn this around, this measurement, and turn this into a measurement of sine squared theta W. If you assume, the flux of boron-8 neutrinos, and you use the standard model prediction of the sevens cross-section, you can actually turn this into a measurement of sine squared theta W. Now, talking about sine squared theta W, that has normally been, again, the purview of high energy physics experiments. But there's another way, to get at that weak mixing angle, and that is through Muller scattering. So this is a parity violating experiment where you use polarized electrons shooting off a target, and you look for an asymmetry here with right-handed or left-handed electrons, and you measure this asymmetry. This asymmetry is tiny. The expected asymmetry is expected to be 32 parts per billion, but the Muller experiment aims at measuring this to a precision better than 1 part per billion. And shown here are some measurements of sine squared theta W as version of log Q. So here are the high energy physics experiments, but the future measurement of Muller will really have the ultimate precision, in this parameter. If at the end of this run, they will be able to measure this parameter to better than 1 per mil. Now, you know that if you probe these couplings, you get very sensitive to higher energy dynamics. And that means you can probe for physics really beyond the standard model. So here's an example of, a model where you have another dark sector with a Z boson of 15 GeV that would modify, the value of sine squared theta W. And if you don't see a deviation from the prediction from the standard model, you can really probe very high energy scales. In this particular case, you can go to 27 TeV. And these are energy scales that are, out of reach, I think, even out of FCC-EE. Now, there are other probes, a complementary probe is also to look at the CKM unitarity. I think we all know that there is tension in the CKM matrix if it's unitary. And the most prominent tension is in the first row, and especially in VUD. So this plot shows you what the tension actually is. So on the horizontal axis is the ratio of the axial versus over the vector coupling constant. And there are two measurements here of neutron decays that disagree with each other. And then in the neutron sector, we also have two measurements of the neutron lifetime. One measurement based on a beam measurement and the other one on a bottle measurement. And the difference between these measurements is a whopping 8 seconds. Now, the most precise measurement of VUD, so the most precise measurement on, the unitarity of the CKM matrix in the next 10 years will come from a measurement of the angular correlations of the decay products of a neutron. And again, this is a project that falls under the purview of nuclear physics. So here are some of the experiments that are actually trying to address this issue. Then, of course, we have other probes that probe, beyond the standard model physics. And one of it is electric dipole moments. There's a lot of searches going on for electric dipole moments. Again, most of them in the domain of nuclear physics. And if you measure these electric dipole moments, you can confront it with many theories. And, from these theories, you can then extrapolate that to what the implication is on the new physics. Now, so if you set an upper limit on these electric dipole moments, the reach of these measurements in terms of the energy scale of the new physics is really very, I think, impressive. So shown here, for example, is the energy range for new physics that is in the thousands of TeV on the current limit of a neutron electric dipole moment. And this is what you expect for the future if you don't observe, an electric dipole moment for a neutron. And as you can see, there are many other measurements that you can do to probe for new physics. In high energy physics at the moment, there's a lot of interest in atom interferometry. Now, another probe, which I call here an orthogonal probe, is actually neutron interferometry. So in these processes, you take a neutron, it's a wave, you split it up, and there are two paths for a neutron to travel, and then you look at the interference pattern at the end, and you look if there was a difference, in the interaction, in one path versus the other. There are many ways to look at this interferometry. There's, for example, phase grid interferometry. And in this particular case, what I've shown here is Pendellösung interferometry, where you take a neutron, you split it up, have it go through a perfect silicon crystal, and then you're sensitive, for example, to deviations from Newtonian gravity. So here on the right, you see a plot of the coupling strength of the additional term, as a deviation of Newtonian gravity. And you can see that you get very, small coupling terms versus the penetration depth. So these are world-leading limits, in a broad range of physics where, nuclear physics is, again, very complementary to high-energy physics. I want to say a few words about the instruments. So many technologies were, originated in high-energy physics, but at the moment, we find ourselves in a position where I think the boundaries between high-energy physics and nuclear physics are really becoming blurred because there's a lot of synergy in the development of these instruments. But let me give you a few examples of these instruments. So one is, the development of the time projection chamber that clearly came out of high-energy physics. So the first one was the development of the TPC for PEP4 at SLAC. Then, it was taken to another level for the TPC for the Olive experiment. But it really was nuclear physics that brought it to an unprecedented scale. So on the left, you see a picture of the TPC of the STAR experiment. And the largest TPC to date, gaseous TPC to date that was built was for the ALICE experiment, and that has a volume of 90 cubic meters, this TPC. Another example is monolithic active pixel sensors. Monolithic active pixel sensors are a very hot topic these days, They arose from a generic R&D program, but then was more targeted towards, nuclear physics. And I would like to remind people that the first MAPS detector was actually deployed in a nuclear physics experiment. That was the STAR detector at RIC at Brookhaven. And again, the nuclear physics community is the one who has really taken it to the next scale. So here you see a picture of the ALICE inner tracker system. That is a 12 gigapixel detector. And they are really, pushing it further. And this is what I mean now by the boundary between high energy physics and nuclear physics is really becoming blurred, because this is really a collaborative development to take it to the next level, where these MAP detectors now are so thin that actually you can build curved silicon detectors. Now, these detectors will play a critical role moving forward for both an EIC and an FCC. So, all detectors that are, being designed these days use a MAPS detector, as their vertex detector. And why do I say that they will play a critical role? Because, they're very important to map the couplings, of a Higgs to the various particles. And because there's a lot of emphasis now on flavor physics with FCC-EE, they will also be able to study these tensions in the area of flavor physics. So in this particular example, B to S mu mu, where here's a standard model prediction, and you can see the world average. And this tension will only be resolved, through very accurate vertexing and tracking detectors. Another example is the development of imaging calorimeters. So this came out of the linear collider community, was adopted by CMS, but now really is the basis for the forward calorimeter for the EPIC detector. And of course, also the readout electronics is currently a joint effort between the high energy physics and the nuclear physics community. A few words about the facilities. There are also facilities that are common, between high energy physics and nuclear physics. One, which I think is actually quite nice, is the accelerators themselves. So the prime example here, I think, is the LHC, where, we have two multi-purpose experiments, Atlas and CMS, but there's also a dedicated heavy ion program with the ALICE detector that really shows you again, how you can optimize the overall program. Test beams are a foundation for the detector development, and they are normally provided by high energy physics laboratories, but currently they're also provided by laboratories that are mainly in the BES area. And then, of course, we have the other facilities that are more generic. They don't belong really to a certain community, but they really, provide the foundation for some of the development of our detectors that we have. Now, the synergies, I think, go beyond just HEP and NP. We had already, I think, good synergies between with Oscar also, and those synergies and as collaboration is even being strengthened today through projects like the Genesis project. So Genesis really brings not HEP and NP, but all of the Office of Science together, and not only all of the Offices of Science, but even all national labs are being brought together under this mission. We also have an example of, the synergies between HEP and NP and basic energy sciences, especially in the area of microelectronics. So microelectronics has really been pushed, by HEP and NP, but the development of the pixel detectors have really led to the development of these pixel detectors for the light sources. And here is a spectrum of detectors that are being developed, in this particular case, by SLAC, which really shows you again the synergies that exist, between the efforts, within the high energy physics and the nuclear physics community beyond those two offices, in this particular case with basic energy sciences. Another example is, how the communities can work with national security. So shown here is an example of the EOS detector, where it really, targets science missions, not only with NP, two areas of high energy physics, but also is very useful for, national security, because the development of these detectors, allow us the near surface detection of neutrinos, which is important for national security. Now, let me give you one, what I think is a cute example. At the moment, we know that there is a lot of emphasis within the Office of Science, on fusion. And there's renewed interest in muon catalyzed fusion. So that is where you have a muon that actually, will catalyze this fusion reaction. So you have a muon beam coming in. The muon beam forms a muonic atomic atom with the tritium, and then it merges with the deuterium. And because the muon is very heavy, it will decrease the Bohr radius. So it will increase the tunneling probability between the deuterium and the tritium, and spontaneously, give us this fusion reaction. So here you have, the muons and the muon beams and the atomic muonium are really in the purview of high energy physics. The fusion reaction itself and the neutron detections that come from this fusion reaction are the purview of nuclear physics. But the way we do this, the reason why we do this is for fusion. So let me conclude that, I think we are at a remarkable time, that the quest to find the missing pieces of the Standard Model is really incredibly exciting. And we would like to get the answers to our questions sooner rather than later. And some of the examples that I provided here will provide the answers within the next 10 to 20 years. Now, science is by its very nature interconnected. It's like the Borromean rings, right? So if you cut one, they all fall apart. And this holds especially true for closely related fields of nuclear and high energy physics. And I believe that there is tremendous strength in working more closely together across the whole of the Office of Science, of course, respecting each other's mission. And through stronger inter-office collaboration, I think the program can be more strategic and because of that, more impactful. So thank you very much.
Thank you very much, Marcel, for a really interesting talk. We have at least three questions for you on the live document. From Heidi, 7 seconds for the neutron lifetime is getting into a region where it would affect early universe isotope ratios. Do you have any comment on this?
That is a very good question. I am not familiar with that, so I owe you an answer to that question. I'm very sorry.
Okay, from Kendall Mon, can you speak to where in the past we've not done a good job of inter-office collaboration? This poses an opportunity to do better now, and how?
Thank you, Kendall, for that question. I think we have all experiences where the stovepiping within the offices has hurt us. I think there are plenty of examples that I can mention, but everyone will, of course, have their own, examples of where we felt that, better collaboration between, various offices and blurring the strict lines between the various offices would have helped us. There are, efforts here where that I think are very good examples of how things are moving in the right direction. And here I would like to give a lot of credit to the detector R&D program within the Office of High Energy Physics that is really making a very concerted effort to blur the lines really between all the offices. In the last example that I gave, with this water-based liquid scintillator detector, it's really a collaborative effort between HEP, NP, and even NA22, so national security. There is again, I think we should move more in that direction. I think the field is moving in that direction, but we can certainly do more.
Thank you very much, Marcel. We have a couple of comments that have been written into the live document, but they're not directly questions to Marcel, and they're fairly long. And because we're a bit late now, I'm going to just encourage everyone to read those comments that are in the live document, and we'll thank you, Marcel, and we'll go on to the next speaker.
Okay.
Thanks a lot.
Thank you.